All right, so welcome everybody to Hoon School Live, Lesson 7, the final lesson of Hoon School. So very excited for the content today. We're just going to wrap everything up, teach you some more things in the standard library, and teach you how to make production-ready code. So yeah, it's going to be a good lesson. So let's start by learning a few more data structures that are going to be pretty useful. So in Hoon, you've probably seen that the character sig stands for the value 0. Like if we cast this to an atom, we see that it's a 0 underneath, right? And it's not a null value. It's not like null or empty. There's something there, and that something is a 0. However, suppose that we wanted to write like a database, right? And we have names linked to values in the database. And sometimes the database can like have something empty, right? You look something up and it's not there. So how do we represent that? You wouldn't want to represent it with just a sig, because that'd be saying like, oh, something's there and that something is a 0. So we want to differentiate between these two, right? So in Hoon, this is solved by something called a unit. One moment, let me adjust the chat. So what is a unit? Formally, the word unit in Hoon is a mold generator. Same as list. We learned about list, right? So it's a gate that takes a mold as input and it returns a mold, right? So you applied like sandhap list pat rs to get a type that's a list of pat rs, or like this, right? So same, you can apply the term unit to something to get a type that's a unit of that type. And what is a unit? Unit is a type union of either just sig or a cell of sig and whatever mold that you called it on. So for example, this is valid as a unit pat rs. This is valid as a unit pat rs, but just the number itself is actually not valid as a unit of pat rs. To put something in a unit, you can either just manually construct it like this, or that just creates a structure though. To make the compiler convinced that it's a unit, you can use this library gate called sum. And that'll make it be a unit. And if you want to extract the value from that, you can use need. So just like this. Oops. So we put the number 2 in a unit and we extract it by applying need to get 2 out. If need is given an empty unit, then it fails. So and there's also a sugar syntax for this, which is just this tick 2 or tick whatever. You might see that sometimes. So there's also an interesting trick with units. So there's a gate called bind. Bind takes a unit and a gate, and it'll make that gate become something that works on units. So for example, let's check out this code here. So we're calling bind on the unit of the cell 2, 3 and the gate add, and it'll make that add operate on that 2 and 3 and return 5 in the unit. And if it's given an empty unit, it'll just return an empty unit back. And this will be useful later. So it's not immediately obvious why you put these things in these units, but we'll see later where these are super useful. So another important data structure we should learn about is maps. So key value pairs or dictionaries are a really important construct in any programming language, right? So lets you store data under a certain name and then look up that name later and get the value out, right? So here's like a key value pair table of like car makes and their models, right? In Hoon, these are implemented with what's called maps. So the term map is also a mold builder like list. It takes as input two different molds, and it creates a mold, which is a map from the first one is keys and the second one is values. So to make a map, we are going to use the standard library gate Y. So let's suppose we're making some like front-end app and we need to store the hexadecimal values of some colors, right? So we can use this, oops. There we go. I'll put it in the chat. So my takes as input a null terminated tuple, right? That's what lists look like. It's a tuple with a null at the end. And this is sure syntax, remember? And each of the elements is a pair. So the head of the pair is the key and the tail of the pair is going to be the value. So here we have red, this, green, this, and blue, this, right? And what that returns to us is this structure, which is basically, that's a map with these keys and these values. We can verify that it's mapped by casting. Here we have this ket-hep, the mold of a map from pat-key to pat-ux, and this structure we just created with mod. So if we press enter, then it works. So that's just creating a map. We'd like to know how to use a map, right? Like put in values, look up values, delete values, and so on, right? So in Hoon, there's a core for handling all these operations on maps. That core is called by, by. So we'll show you several different operations that you can use with that. And recall that when we were doing things with cores, like we used sentis to make a new copy of the core with just some value, some part of it changed, right? And when we're operating on maps, it's going to be a similar thing. We're going to make a new copy of something, but it has some change made to it, right? So let's demonstrate how to take this map and put a new pair in it. But first, we should recall last lesson we learned about these gate building doors, right? So we have this door where you could pass in two numbers and it built a linear equation gate, right? So just to recap, we'll go through like what was happening here. So this outer door takes a sample, which is a pair of A and B, has a single arm. That arm contains a gate. That gate takes a sample X and also uses A and B from the outer door, right? And we could make a gate representing like 4x plus 2 or whatever. And we could also call that gate on some input. So here we built this gate with the inputs 4, 2, and then we called it on the input x equals 1. And you get 4x plus 2 with x equal 1 is 6. Right? So when we're going to be working with maps, the same pattern is going on. What's going on here is we have this door by, and it has an arm put. And we pass the sample to the door as colors, which is our colors map that we just created. And this expression creates a gate. And that gate takes the key value pair and returns a new map with that key value pair added. So let me show you what's going on. I'll put this code in the chat. So here we declared this map with my, right? And we set it to colors. And then we said, let colors be calling this gate, this gate that came out of doing put by colors, call this gate on the pair yellow and this hexadecimal for yellow, and then return colors. What we get is this new map, green, blue, red, and yellow is here too, right? And we can show that this just created a new copy of it. Remember, this notation skips the first match to a face and gets the second one. So if we, even if we put yellow in this new copy, if we do ket colors, we get the original copy that doesn't have yellow in it, right? And just to remind us again, so this is a door that lets us work on maps. This is an arm of the door. This is a sample to the door. This whole thing created a gate. We gave that gate a pair, and then it created colors with that pair added to it, right? Are there any questions on that?
Yeah, I'm actually really curious as to how maps are implemented under the hood, since everything is a binary tree.
Yeah, so what's going on here is this NLR is basically like a binary tree representation of a map. So we have L is like what's stored in the left node, and R is what's stored in the right node, and N is like what's stored there. And I don't know what the particular algorithm is to take a map and like where to put them in the tree is, but there is some algorithm there going on. So yeah, they might be jetted. I'm not entirely sure on that. But yeah, they are definitely stored in a binary tree. That's what this means. So yeah. So let's take this map and show how to delete something from it. So same as before. Del is an arm in the by door, and we pass our colors map as a sample to the by door. This expression creates a gate which takes a key and returns this colors map with that key deleted. So let's show it in action. Here we have colors set to our original map. Let colors be calling this gate on the key green and return colors. And here we just have the map with just blue and red, right? If we pass in a key that doesn't exist, then it'll simply return the original map unchanged. So here we have orange, and yeah, everything's still there. We can look up the value associated with the key with get. So get is an arm in this door. You call it with this sample, which is the map. This creates a gate which takes a key, and if that key value pair exists, it'll return the value in a unit, and otherwise it'll return this sig. So here we're using the unit that we just learned about, right? So colors is our map. Get by colors proves the gate. We call it on red, and we got this this hexadecimal, right? And if we call it on something that doesn't exist in there, we just get this sig. You can also use got, which works just like get, but it directly returns the value instead of wrapping it in a unit. But you have to be careful with this because so here it's not wrapped in a unit because we use got, right? But if we call it on something that doesn't exist, then you actually get a failure. So you want to be careful with using this in production code. Something useful is you can convert a map to a list and then operate on it like a list. This is with this arm tap. So this doesn't return a gate. This actually just returns what you want, which is the map as a list. So let's see it in action. So we set colors to be the result of this my, and then we run the arm tap of the door by with the sample colors, and we get this list. If you want a list of all the keys, you can use key, which is pretty much the same syntax. Here's all the keys, and you can get all the values with val, the same syntax. Here's all the values. And just like with lists, there's a really rich library of utilities for working with maps. For example, there's earn, which is like turn, which is like applying a gate over all the entries, right? We don't have time to go over all of these, but they all exist in the standard library, and they're all here in this link. If you want to look at it. All right, so that is the conclusion of the section on maps. Are there any questions on that? All right, there's no questions, I'll keep going. So when using got on a key that doesn't exist, it crashes because you're asking it for something that doesn't exist. So it's like look up. Well, right. So why wouldn't it return sig? Because sig is a value. And if you did got on a map and it returns sig, that would tell you, yes, this key existed in the map and its value was 0. So how can you differentiate between a key existing and its value is 0 or just sig versus that key actually doesn't exist, right? Because you could do like got lets you skip this. Why would someone use got over get? Because it lets you skip the step of like unwrapping something from a unit. So if you know something exists, it's faster, but get is safer if you're not sure that something exists. So like I can, as an example, I can just like, yeah. Here, green, make this type safe and make them all sig. So see, this is a valid map, right? And I can do like colors be this thing and dot by colors red, and it returns sig, but that's saying red was in there and its value was sig, right? So if we did orange and if that returned was sig, you wouldn't be able to tell if orange was there with the value sig, right? All right. So if there's no more questions on maps, I'll be moving on to another data structure. All right. So suppose you'd like to keep track of who you're inviting to your birthday party, and you keep adjusting the list of invitees, sometimes adding people, sometimes removing people, sometimes you add someone again just because like you thought you might have forgot or something, right? And if you store this on a computer in a list data structure, a list could contain the same thing twice, right? And you wouldn't want to accidentally send somebody 2 invitations instead of 1 because their name was on there twice. So a data structure called a set is perfect for this situation. And a set is an unordered grouping of data in which each entry is unique. And by that, I mean it only appears once, right? So formally set, the term set in Hoon is also a mold generator, and it takes as input a mold and it returns a mold, which is a set of that mold. So here it would create a mold, a set of tapes where each unique tape can only appear once, right? To create a set from a null terminated tuple, you use sy, psi. And here, note that we have this input list of Alice, Bob, Charlie, Dave, right? But in the resulting set, Charlie only appears once, right? So remove this duplication. And there's a door for working with sets, just like there was a door for working with maps, right? So it's called in. Let's show how to put another element into our set. So we use the put arm of the indoor, and we pass it a sample, which is the set we want to operate on. This returns a gate, which takes an element, and then returns the set with the element added, right? So, all right, let's try to add someone named Emily to our part. And this, as we just mentioned, this output with these N, L's, and R's is this is referring to the underlying data representation of the set. So this is structured as a binary tree. It's a bit hard to read, but if we cast the output to a set tape, then it's much easier to read. So Alice, Dave, Emily, Bob, Charlie. So maybe you remember that last time Dave was at your party, he got drunk and set something on fire. So we'd like to remove him from the party list, unfortunately. We can do that with the del arm of the in door. So works the same. We call this arm of the door with this sample, which is the set we want to operate on. It returns a gate, which takes an element and returns this set with the element removed. So here we create this party set, and then we call del in party on Dave, and we cast that result to a set tape just to format it nicely. And we get the set with the element removed. You can use the has arm of the store to check if an element exists in the set. So let's see if, so again, you call this arm of the door with this sample, and that returns a gate, which takes an element and returns send.y if that element is in the sample, and send.n otherwise. So let's call this on Frank to see if Frank is in the set what we created, and we get a no. And if we call it on Alice, then we get a yes. You can convert a set to a list using tap. So calling the tap arm of the store with this sample just directly returns this set as a list. And something kind of interesting happened here because here this original list had 2 Charlies and this output list just has 1 Charlie, right? So something useful you can do with this conversion to a set and back is just use it to deduplicate a list. So just convert to a set and back using this arm, and you get a list with all the duplicates removed. And you can also apply a gate to all the elements of the set, just like turn for lists. So for whatever reason you want to capitalize everybody's names in this party set. So the arm run of the indoor, you give it a sample, which is the set you want to work on. This returns a gate, which takes another gate, and it returns this sample set with that gate applied to everything in there. So here we create this gate, we pass it cuss, and then we get the set with everything capitalized. As with maps and lists, there's a lot more utilities that we don't have the time to cover entirely, but you can see all of them in the standard library here. Are there any questions on sets? All right. So there's a few more common data
Okay,
structures.
sorry, I have a question.
Yeah.
Is it the same here where like the only reason you'd use a set over a list is efficiency?
Is there an efficiency gain? Well, they're both structured as binary trees. But the reason you use a set over a list is because a set has unique elements. So you don't want like duplicates
Okay,
there. That's the main reason. It's also unordered, whereas a list is ordered, but I don't see where that would be like an advantage necessarily. So yeah.
okay, thanks.
Can you add sets? Yes, there is a utility to make the union of two sets. I didn't go over it, but yeah. It's on here somewhere. So there's set difference, and there is uni, produce the set of a union between two sets of the same type. So this is adding two sets. All right. So there's a few more data structures. Can I use the add gate to? No, you cannot use the add gate to add two sets because that's like kind of a categorically different thing, right? A gate is taking an atom. That add gate is taking an atom and adding like the underlying number, right? But these are like data structures, so you want to use the add gate on a set, right? So there's a few more common data structures that I think what happened was people just end up using these things a lot, and they decided to make standard library utilities for them. So a jar is a map whose values are lists. A jug is a map whose values are sets. And a mop is a map with an ordering over key. So it's like kind of a combination of a map and a list. And we're not going to dig into these in the lesson, but it's good to know that they exist. And there's also utilities for working with all three of those. All right. So something that we saw a bit before, this Zapgar rune takes a noun and returns a vase. And a vase is a cell of the head is a type of the noun and the tail is the noun. So if we do like Zapgar 2, you get a cell of Pat UD and 2, right? And also there's this Zapgal rune. So you'll use these a lot when you start working on apps or working with a system. Vases are used a lot for transmitting data like over the network, for example, or between apps. So Zapgal, that takes a type and a vase, and it tries to extract the value in this vase into this type, and it crashes if it doesn't fit. So this is like you have an app, you received a vase from somebody, and now you're trying to unpack that vase into a data structure that you can use, right? So for example, I made a vase with 2, and I tried to extract it with Zapgal into a Pat UD, and that's going to work and return that 2, right? But if I try to extract this vase with 2 and a type Pat UD into a Pat P, that's going to fail. All right. So for people with experience in other functional programming languages, we're going to go over a few tricks that are going to be familiar to you from those languages. And if you're not, then don't worry at all. Just remember these as some tricks for modifying the behavior of gates. So have you ever wanted to call add or mul on more than 2 arguments? You actually can if you use this rune. So mccoll takes a binary gate and modifies it to take as many arguments as you want. I think I have the numbering wrong here. So, but yeah, so let's go over an example of using this. Here we call mccoll. The first argument is the gate mul. And then all the following arguments are everything you're going to pass to mul. And you close the run with the statistics, right? And that just multiplies all of them. Pretty straightforward. And there's a sugar form of this, which looks like this. And that's just this col in front of these parentheses. So you might have heard of the term currying before. What this means is in Hoon taking a gate and freezing one of its arguments to be a certain value. And this creates a new gate, which already has one argument passed in. So it takes one less argument. Let's see an example of this to see what we mean. So there's a standard library gate, curry, C-U-R-Y, which will bind the leftmost sample of a gate. So here we define mole 10 as currying the gate mole with the value 10. And if we return mole 10, that just returns a gate, right? This is a gate which takes one argument. We can define it and then call mole 10 on 4, and then we get 40, right? So like that should be pretty straightforward. There's also a right curry. So this binds the leftmost sample, and you can also bind the rightmost sample. For example, CURR binds the rightmost sample. Here we're currying the gate greater than with the value 10. So GTH-AB says if A is greater than B, right? So this is going to say if something is greater than 10. And then we can call it on 11. And we'll get a yes. 11 is bigger than 10. Any questions on that? All right. So we're close to wrapping up the Hoon section of the course. Before I do so, I want to go into a few more syntaxes that you might see around in different kinds of Hoon code. So you've already seen this pat, right? And this just is a mold, right? This is a generic mold for any atom. Like if you see in a gate, like A equals pat, that means you're getting an argument A, which is an atom, right? What this ket means is the same thing, but it's a generic mold for a cell, any pair of values. And what this tar means is a generic mold for any noun, so any sort of data structure in Hoon. And what this means is a generic mold for a Lubian, which is a yes or a no, right? And we can produce the bunt of these. So call that ket-tar produces a bunt, a default value. Here we get 0, 0. We can produce the bunt of a noun, which is 0. We can produce the bunt of a Lubian, which is just yes. If you ever see a notation that looks like this, you might at first, why isn't it called a Boolean? That's a good question, because the creator of Urbit decided to make 0 true and 1 false, which actually has precedence in a lot of different like philosophical systems, but in most languages, 0 is false and 1 is true. So instead of a Boolean, he called it a Lubian. So that's an interesting factoid for you. So if you encounter these sorts of notations, you might first think there's some sort of mathematical operation, but that's actually not the case. This is shorthand for creating different kinds of cells. So 1 plus 2 does not return 3. This returns a cell of sen 1 and 2. So, for example, this first thing is going to be a term, and the second thing should be a value, right? So we can do plus the text dash end, and we get this hat plus main coon, get that, right? And the slash notation is the same thing. It's literally just a duplicate notation. This ket notation makes a cell from the two things. So if you do 1 ket 2, that's not 1 to the power of 2, that's a cell of 1 and 2. If we do A is Alice, B is Bob, A ket B, you get a cell of Alice and Bob. All right, any questions on that? Ket notation, yeah, it's cute. It's people use it for this and that. You'll see it. Hoon developers, there's a lot of them who like using these like cute little sugar syntaxes. So yeah. All right. So before I get into the next big topic for today, I'm going to turn on my AC. So one moment. All right, I'm back. So the next big topic for today is going to be something called say generators. So far we've learned how to work with regular generators. We've written them, we've saved them, and we've run them from the command line, right? The say generator is the next level up for writing generators. So first, let's look at a simple regular generator. I'll post the code here. Let's take this code. And what does it do? Well, it accepts a tar, which is just any noun, right? So this gate takes anything and just returns add 40 and 2, right? So if we save this in our gen folder as let's call this test.hoon. And then we run commit send base and just run less test. Well, if we just do less test, this actually gives us an error because it's expecting to be passed an argument. It doesn't do anything with the argument, but it's expecting something. So you need to give it something. It doesn't use it, but like whatever you give it, it's just going to return 42, right? Because it just throws it away. Let's write this code as a say generator. Save this, commit. And now what happens if I run less test? It actually just works without even passing in any arguments. So that's kind of interesting. Let's look at this code and try to understand what's going on. So up top, we have this Cohort. This is creating a cell, right? We're creating a cell of sensei and whatever this outputs, right? Whatever this gate outputs. This gate takes a noun, which it doesn't do anything with, and then it returns a Cohort, a cell of send noun and whatever the result of the gate is, right? So what's actually going on is this structure is going to produce a head of sensei and then a tail of send noun and the result of the gate, right? So we can see how this corresponds to this, right? However, when we run this in the dojo, these tags are metadata information. These, you don't see these when we run this, right? We just got 42. So these are metadata information that's processed by the system, but this is just the actual result and what we get. So let's try to understand what a say generator is more broadly. So in our code here, we just have this tar, right? We're saying the argument is any noun and we're not really using it. However, say generators have actually a highly specific structure to their arguments, and that structure gives them access to system information that regular generators don't get access to. So the sample to a say generator is in general a triple like this, right? So the first thing in this triple is another triple. It's a triple of now, any, and b. So what are those? Now is the current time. So the generator can get access to the current time. This is passed in by the system. You don't pass it in from the command line. It just automatically gets populated. Any is environmental entropy, and this is used for generating randomness. So this actually comes from Linux. Linux has something called CPU jitter, which is like the random movements of your CPU. And then this gets passed to your Urbit, and your Urbit uses this to generate random numbers. So say generators can use randomness, while regular generators don't have access to that entropy. And finally, this beak is the current path of like where you are when you call this generator. This has three parts, which is your current ship, like sample palnet, or in this case, Zod, the desk you're on, which in this case is base, and case is a clay revision number. So like what is the most recent version, or what version of this file or this location are you looking for? And usually you just have the most, like a recent date when it's here. And again, this is passed in by the system, so you don't explicitly pass this when you're calling the say generator. Next, the next thing in the triple is a list of unnamed arguments. And this is a list where you specify what arguments are required for your generator. So anything here must be passed in, otherwise the generator call will fail. And finally, we can actually specify optional arguments to a generator. And you can call them with this syntax, or you can call them without, and with or without, either way it'll work. So that's another thing that say generators can do that regular generators can't do. All right. So we mentioned that this any argument in a say generator lets us use randomness. Let's go through an example of that. So here I have some code in a paste bin. You can follow along if you'd like. And I'm going to take this code. I'm going to save this as dice.hoon in my gen folder. And I'm going to run commit. So let's go through what's going on in this code, right? So first we have a cell of sensei and a gate, and inside the gate is a cell of send noun and whatever it produced, right? So this is just, these are the tags that are telling you this is say generator. Next we have this triple, right? These are the system arguments of now, any, and beak. Next we have one required argument, which is n, which is a number, a PAT-UD, right? And finally, we're saying we also have one optional argument, which is bet, which is also a PAT-UD. This code right here, what this does is it takes this any entropy and this n, and it generates a random number between 0 and n. And this bet here is that was optionally passed in, and the generator just returns a cell of these two things, right? So let's try this out. We ran commit. Now we can do less dice 6. And we get 3, 0. So we can try this again, right? 0, 0, 5, 0, 4, 0, 3, 3, 4, 4, 1. So yeah, we're getting random numbers. And notice that the 0, since you didn't pass in this optional argument, it just used the bunt of a PAT-UD as the optional argument. So how does this random number generation work? Let's go into that a little bit. So again, we have a door, which is kind of like a library. And we were using this door, this OG door deals with random numbers. We pass as a sample to that door, any, which is our environmental entropy. And this is just a big number, really. So you could pass in any number like 0 or 1 or whatever, but we decided to use this big number that we got from Linux, right? And we're calling this rad arm of it. This whole expression creates a gate, which takes a PAT-UD and returns a PAT-UD between 0 and this argument. So here we created this gate here. Then we called this gate with input n, and we got a random number. And so that's how we got these random numbers for our dice generator. And if we wanted to give it that optional argument, you have to do this comma here to separate the named required arguments from the optional ones. There you equals bets 100. The random numbers are between 0 and 6 because we're passing this input 6. We can do like we can do a 100-sided die. Like I just did 6 because like we're used to 6-sided die, right? So where in the code is the RNG limited in that range? So as we mentioned, so we passed in this n to this state generator. This n is used right here, right? We call the rad arm of the OG door with any as a sample. This creates a random number, but it's not, there's no limit. Like this is a very big random number, basically. And then this, or this creates a gate. I'm sorry, this creates a gate which can produce any random number. And then passing the n as input to this gate is what creates a random number between 0 and n. So here is where rad OG any taking n as an input is where that limit is created. For example, here let me explain this a little better. So here we can just pass 0 as our entropy, right? It doesn't matter, like we can use anything, but this is just a seed for the random number generator. And then if we pass 100, then we're going to get a random number between 0 and 100. We can give it a different random seed, and we get another random number between 0 and 100, right? We can like, oh, it's the same number. So yeah, like, yeah. Is any completely dependent on how the underlying OS implements randomness? Yes, because it's getting it from Linux. So Urbit itself is a deterministic solid state system. So it's just like whatever input you give it, it's going to operate using that input, right? So it's talking to the OS to get that any, and it's dependent on how Linux implements that. Yeah. All right. So any more questions on state generators? Cool. Seems that any is like a generated seed for randomness calculations. Yes, exactly. Any is a random seed. That's right. All right. So for the following section, let's look at a new piece of code. I wrote a gate which takes an input and returns all of the prime numbers between 2 and that input. So let's take this gate, save it as, and it's in the chat, by the way. Save this as primes.hoon in our gen folder. Run commit send base, and then call it primes 10. And we get all the prime numbers between 0 and 10. Primes 40 gives us all the prime numbers between 0 and 40. Off topic, but are there any attempts being made to interpret knock directly on OS? Yes, there are. Actually, someone is trying to make knock PU. The folks at Native Planet, there's somebody working on that, and it's very interesting, but that's a far off target because it works just fine on Linux, and everybody pretty much has Linux and can access that to run Urbit. So immediately, like for the short-term future of the project, having your native hardware or native OS is a high effort, low reward, right? But like maybe in the future when Urbit is much bigger, then this will be a higher priority. Well, the ZK knock thing is different. Yeah. Zorb is a different thing. Yeah. Oh yeah, they're working directly with knock. That's right. I think they're making a virtual machine, but I don't know too much about what they're doing. But anyways, so we have this code, this generator, primes.hoon, takes an input and returns all the prime numbers between 2 and that number, right? So when you're building like production code like this, it's really important to include comments, right? Like it helps other people read your code. It helps you read your own code. And to include comments, you simply use the col root. So works like this: you do a col, and everything else on that line is interpreted as a comment. It doesn't do multi-line, so every line that you have a comment, you need to put another col, right? It's like that. And here I have this like very commented out version for you guys. So if I wanted somebody to read my Hoon code, this would be like the optimal way, right? Like there's comments at every step. This is considered proper style. So yeah. When we're building complex pieces of code, there's a lot of tools that we can use to make sure things are working correctly. For example, in our primes example, it wouldn't make sense. Can you use col with a gap on the end of the same line? I'm not sure what that means. Like a gap, like 2 spaces like that. That's fine. Oh, like this. Yes, you can use col on the same line like this. Though some people have said like this is not like that encouraged, but yeah, you can use it on the same line as some code. That's totally fine. So when we're building complex pieces of code like this, there's a lot of tools we can use to like test various parts of it and make sure things are working. For example, in this code, like it wouldn't make sense if our input number was 0 or 1 because the smallest prime is 2, right? So we can use this rune called whatgar to catch that. So I think we learned this rune before, but basically whatgar rune says assert that a condition is true, otherwise crash. So here we're saying assert that input is greater than 1, otherwise this will crash. So if we save this, commit, and we pass in primes 1, oh, it's crashing forever. Yeah, we get a failure because it's failing right here. And we can even see line 7. Oh, it's even failing for that, but we put it here. There we go. There we go. Failure on this line. It says failure occurred, line 7. So there's another rune that you can use to assert things. So what gal says assert a condition is false, otherwise crash. So just the opposite of this. Let's assert that it's false, that the input is less than 2, right? and give it a 1, a failure, you give it 10 and it works, right? So this is just catching that. And we learned the zap ring, right? Which just says crash. So here we can rewrite this with zap. This is basically the same thing. Let's say what call if input is less than 2, then zap crash, right? And we can print out an output to the terminal upon crashing. So this is going to be super useful. And we can do it with this rune called sigbar. Takes 2 children. And if the second child crashes, it prints the first child, right? So let's put this sigbar and this tape crash because the input was less than 2 right before the rest of our code. And so if we commit and then we do less prime is 1, we get this nice error message, crash because the input was less than 2. And if we don't crash, then there's no error message. If you always want to print something out, then there's also a room you can use, which is sigpam. It's pretty straightforward. It just always prints the result of this first child and then does the second child. So, for example, let's say I want to keep track of this list, which I'm operating on in this trap here. So I can do sigpam output, which is the name of the list. And now if I run my code, commit and run my code, oops, then I get these outputs, right? That's pretty nice. So this is all the intermediate steps of that list that's being looped over, and then finally we get the result, right? So that's a super useful trick for whenever you're coding. All right, any questions on that?
Yeah, so just can you repeat? So it pretty prints the first child and then runs the second child.
Yeah, in this case, the first child is just output. So an output refers to a list that we created. So how this code works is first we create a list of all the numbers from 2 to your input number here. And then we loop over that list, removing everything that's divisible by some number, right? So, and this is saying in every step of the loop, we're going to print output and then just do the rest of the loop, right? So this
in general, it's like it just pretty prints the first child and then runs the second, even if the second doesn't have anything to do with the first child.
Yeah, that's right. Yeah.
Okay. Yeah, I'm just wondering because it's like such a common pattern where you have like a rune and you apply something to the first child and then you just run more code.
Yeah.
So it's not immediately like clear like why that's such a common pattern.
Where you have a rune and you apply something to the first child and then you run some code.
Yeah.
Yeah, because I mean that's just a way of like composing different expressions, right? So like instead of like do this, like do something and then do that. Like you could have made this like some random text, right? And you just print that out like 10 times, 8 times, whatever. But yeah. So you can save code in a core as a library file, and then you can call that library file and use it in your other piece of code. So let's rewrite this code, this primes code, to use a library file. So Dan says, I understand the general pattern as construct context, then run code in that context. Yes, that's, if you're coming from an imperative language, that's a good way to think about it. All right, so let's learn how to use a library file in Hoon. Let's take this code. So, and we're going to say we took all this logic basically and we exported it to this arm of this core, which is going to live in a library file, right? We're going to save this not in gen, but in lid. We're going to call it primes lid. And then we're going to make a new primes.hoon generator file. So what's going on here? Here, this faz_lus room says import something from the library folder. In particular, look for the thing called primeslid and import it. And here, we're saying call the primes2 arm of the primeslid core on the value input, right? So we save this, run it. Same thing happens. I think there's a sig down in here. So it still works. We're just importing this functionality from the library, and we're just calling it here. If we put this tar in front of this library file, then that lets us access the namespace of this core directly. So we don't have to pull it out and compose it. It's just like built in the subject. So we can just do primes2 input. Let's just calling this primes2 arm. All right. Any questions on using a library file? So for this like shorter piece of code, it's kind of like extraneous, but in general, like if you have a bunch of utilities that you use a lot throughout your other piece of code, importing and using a library is super useful. All right, so testing your code is really important part of shipping clean and high quality software. So let's write and run some unit tests for our primes generator. So when using mol_rs, we're saying take mol from the rs library. Yeah, we're taking, when you run that in the dojo, you're saying take mol from the rs core in the subject. So it's the same thing as this. Or like this. It's like that. Right? It's that col is sugar syntax for this. When we do commit base, our functions are immediately available. When you do commit base, generators, anything in the gen folder is immediately available in the dojo. If you want to access a library file from the dojo, you can do that too. You can build it. You need to build it, and then you can access it. I don't have time to get into it today, but yes, you can build a library file and access all those arms from the dojo as well. Yep. All right, let's get into unit tests. So first, what we're going to do is we're going to go to our Zod base. And we're going to create a new folder called tests, right? And then we're going to take this file, this test file, and save it in there. Tests primes.hoon. Right. So what's going on in this test code? Have this library import, this faz_lus we just saw, right? Tar test. So we're importing a library called test, and we're going to use some gates from that library in this code, right? This faz_tis we haven't seen before, but this is a general rune to import any Hoon file. So this is saying, let's go to the file in gen called primes and import it under the name primes. So this lets us access our generator that we wrote so we can test it, right? Here you have a core. The core has a bunch of arms. And all these arms need to have the word test in them for them to be run. So that's why I named them test 01, test 02, test 03, test 04. This expect equal is a gate, which we imported from this library, this test library. It takes two bases and just asserts that they're equal. So here the Zapgar is creating a vase, right? And we're creating a vase of the list 2, 3, 5, 7. And we're creating a vase of the output of primes calling it on 10. So this is saying, if I call primes on 10, I expect that I get a list of PAUDs, which contains 2, 3, 5, 7. If I call primes on 2, I expect that I get a list of PAUDs of just 2. And if I call it on 50, I expect to get this list of these prime numbers, right? And the vase, this vase checks not just the values, but this makes sure the types match as well. That's why this is here. You can also test to make sure your code failures. It does a failure. So that's what this one does. This expect fail is a gate imported from this test library. It says, so bar dot. So the reason we have this here is because we actually don't want to run primes 1 immediately. So remember, this creates a core with a single arm. That's all this does. And so we're storing this code in a core because if we just did primes 1 here, it would actually just crash the test file. So this is saying, let's wrap this failing code in this thing so we don't immediately run it. And then pass it that way to expect fail. So that's kind of an interesting trick. But this is basically saying we expect that running primes on the input 1 should produce a failure. So if we save this file, then we do commit base. Then we can run the tests with this syntax. And we get all the tests passed. Awesome. So, oops, didn't mean to type that. So this syntax here is saying, let me run a thread called test. And we haven't learned what threads are, but they're basically like transient pieces of code. And this is the input to this thread, which just tells you where to locate the file that you want to run. This tis, this is actually a beak. So this is what this is underneath is this Zod base and the current version of the desk. So you use these tis to just like substitute the default values, but that's what it is underneath. The same beak that we learned about earlier. And then the rest of this is just a path file, right? So, all right. So are there any questions on tests before we get to our final topic? All right. So for our final topic of Hoon School Live, we are going to poke around in our ship and try to understand the structure of the system. So here we are in Zod. We have a base desk. A desk is like one version or like set of collected software, right? So each desk contains an entire version of your Urbit ship. And there's a bunch of folders in here. So let's try to understand what all these folders are. This sys folder contains your system files. We'll get into that in a bit. The gen folder, as we've worked with, this contains your generators, which are reusable scripts, right? Lib folder contains library files, which are utilities that you can import and run in other code. The app folder contains files that define Gall agents, which are how apps live. Any app that you install on your Urbit ship is going to have a file in here, and you'll learn more about this later. This Sir folder is linked with apps. So apps have structure files which define like types that they use, and you put those in here. This Mar folder is also linked with app. This is mark files, which these define file types basically, and these are also linked with apps. So your app might say like, I use a certain mark to communicate with the outside world, and I define it here. TED is threads, you'll learn more about those later, but we just use the test thread. So that's what lives in TED. And sys.kelvin basically just tells you, this tells you your current version. So we're on 4.15. And this desk.build tells you all the apps that are installed on your desk. Let's look into sys a little more. So there's 4 files in here. Hoon contains all the standard utilities you've been using. So like add, mul, whatever, like working with maps, lists, they're all defined in here. So the whole language and compilers and everything about Hoon. Arvo defines the basic event loop for the operating system. Lol contains some types used by Arvo, and Zeus contains some user libraries, like working with crypto or JSON or HTML, that kind of stuff is in Zeus. So when you're working in the dojo, the standard subject is basically all 4 of these files composed against each other. So that's what the standard subject is. And finally, inside this folder vein are kernel modules called veins. And these are like discrete parts of the operating system which handle different jobs. Gal.hoon handles agents like apps. Vein handles timers, Dill handles the terminal, and there's a bunch of things. So that's basically, in a nutshell, like the entire Urbit operating system. So as we come to this conclusion of Hoon School Live, you'll enjoy knowing that as far as entire operating systems and network protocols go, Urbit is extremely small and simple. And as a Hoon School finisher, you have a good foundation to start to understand the entire system. So you can't say that about a lot of software projects. Urbit is a growing and evolving system that is always under construction. And don't consider anything you've learned in this course to be frozen or permanent. When we hit 0 Kelvin, maybe that'll be the case, but that's far off, right? So this is a system that can and will be changed. And in particular, you can contribute to the system and help improve it the way that you want it to improve. What is 0 Kelvin? So Urbit operates on a Kelvin decrement system, which is every time there's big changes made to the system, a number decreases. So currently we're on 4.15, it'll decrease to 4.14. And when that hits 0, no more changes are allowed to be made to Urbit.
Oh, that's so interesting. So it's like, it's not that there won't be necessary changes once it hits 0. It's just that's the rule. Like that's like
exactly.
a preset rule.
When it hits 0, you're not allowed to change it anymore.
Oh, that's interesting.
So every time the core devs ship something, it's like it has to be important and like it has to merit changing that number down. So yeah.
Are there any approximations for when Kelvin 0 might happen?
Long time from now, most likely. Long time from now. Yeah. And as a Hoon School graduate, so if you learned all this knowledge, you can be a critical part of improving Urbit and taking us to the next level. Whether that's working on the core system, improving our developer tooling, making a fun app, or starting a company, whatever you want to do, we're here to support you. And if you ever want to consult on what your next step might be on the network or what you might want to do, always feel free to reach out to me. Some ways that you can get involved are, we have a grants and bounty system. You get stars for completing projects. It's very cool. App School starts soon on August 22nd. It'll be at 3 p.m. Eastern and run for 8 weeks. And we also have the hackathon coming up, which starts on August 28th, and it'll go up to a demo day at Assembly in Lisbon. So it's been a great time teaching all of you. I will definitely be in Lisbon. It's always a good party. And we really look forward to seeing you around the network and at the events. And I'm excited to see what great things you guys are going to build with your new school skills. So yeah, thank you for attending. Are there any final questions or anything that you want to ask? I should be at office hours right now, but I guess I can stretch it a little bit. Yeah, thank you, folks.
Thanks, Jack.
Yep,
I just have a question.
yep, go for it.
So we've kind of written all this, so we're kind of going towards apps now and building things. Are there any like build tools for Urbit when we're designing apps and things like kind of in the style of, say, the closest thing I can think of is like Node.js or something? Like, are there tools or standard methods that developers use, or like a stack of tools? Or
Yeah, basically developer tooling right now is sparse, and it's an area that we need. We, as in like the Urbit Foundation, we want to fund more efforts on that. So there's not like a standard stack of things to my knowledge. There are several tools around that help, but there could be much more tools for helping people work on Hoon. So yeah.
okay.
Yeah, any more questions? Yeah, there's the dev pill, which has some useful stuff. That's correct. Yeah, Talon has some useful tools. Yeah, thank you. Thank you, Philip. Cool. Any other questions? Otherwise, I will be at office hours. The homework and the notes for this will come out tomorrow. And as a reminder, you have 2 weeks, so August 26th to turn in the homework. So, and I'll be around. You can feel free to DM me or whatever you like, and I'm definitely available to help you get through the homework. So, yeah. Cool. Thank you guys for being here. All right, so I will end the recording now.